Okay, folks, we can get started. Hope people had a good break. I'll just remind you before we get going, I did the first round of final project purchases on Wednesday. My plan is to do another round of purchases in the event that you didn't quite get your requests up in time this coming Wednesday. So let me just remind you that on the Canvas homepage, there's an embedded Google form through which you can specify exactly what you'd like to purchase. I'll remind you again that I will purchase up to $25 worth of components for you. And so you can use this form to identify up to $25 worth of stuff that you would like for me to get for your final project. You may then, if you would like to, spend an additional $100 of your own dollars on the project, but the total materials cost of the final project shouldn't exceed $125. Any questions about that? I'll ask too, if you can, I think I specified in here, if you can find the product that you're looking for on DigiKey, please try to use that as your preferred vendor. It's just really easy for me to make purchases from DigiKey. I can, of course, make purchases from elsewhere, but if that's an available vendor, that's an easy one for me. Okay. Any questions from about anything else from folks? Any lab report questions or questions about getting started with final projects logistics-wise or anything? Okay, that being the case then, I thought that what we would start doing is, as I mentioned previously, now that we're into final project season, the flavor of these lectures is going to change a little bit. Where previously these lectures have been devoted entirely to helping you in that week's lab assignment, we're now going to start covering topics that will be of potential relevance to a large number of final projects. And so I have a bunch of sort of special topics lectures planned in an order that is informed by your final project proposals. And so I looked at those proposals and figured out what would be sort of the most helpful stuff to cover first, and we'll start with that stuff, and then we'll get to the more sort of specialized stuff as the semester progresses. And so I thought that the place that we would start is with using the Pico W to implement a GATT, a GATT server on the Pi Pico W. This would allow for you to generate a phone-based interface to your final project if you wanted to. I should sort of talk about this in the abstract for just a moment. So a few weeks ago in his guest lecture, Bruce mentioned that there are 3 external libraries that Raspberry Pi has ported to the RP2040. So in addition to the SDK that was written by Raspberry Pi, there exist these 3 external libraries that have been ported to the Raspberry Pi Pico. One of these is LWIP, which is what facilitates communication over TCP and UDP with the Pi Pico W. Another one is the Tiny USB library. And the third one is this Bluetooth stack, BTstack. And that's what I'm going to talk about today. I'll mention, I mentioned a few times throughout this class that a course like this is a constant exercise in trying to figure out what should be exposed to the students and what should be hidden or abstracted away. And it's tricky to get this exactly right. And I've taken my best guess at that with this particular library. It's slightly a challenge. And I'll just mention that preparing all of these materials revealed to me the importance of in the event that you are trying to incorporate some large external code base with your project, it's important to ask yourself before you start doing that, what is your goal in connection with that external library? If your goal in connection with that external library is to become a contributor to it, that is to say to augment it or to improve it in some way, then your aim in connection with that library should be to understand at a very fundamental level how that thing works so that you can build an improvement upon it. If instead your goal is to use that library, the aim instead, it's never a bad idea to have a low-level understanding of how that library works, of course, right? But it becomes particularly important to generate an understanding for what this external library looks like to your application program. When you incorporate it and you plug it into your stuff, what does it look like to your stuff? And what resources does it consume that you need to be careful not to consume in your own application code? That is to say, it's particularly important to generate an understanding of these things that allows for you to guarantee that that your application is compatible with it, that you are not going to use any contended resources and you're not going to interface with it in some way that makes it error prone, right? So it's important to generate sort of an understanding of this thing as it appears to our program and to understand what it consumes. And so that's going to be the flavor of the conversation that I'm going to start today and perhaps continue on Wednesday. And because of that, Bluetooth, I'm going to give you just a very, very brief description of the whole Bluetooth stack here. But it is a stack. It includes a whole bunch of layers. For purposes of our conversation, which is trying to write an application that's compatible with BTstack, this external library, most of our conversation is going to center upon the top of this stack. This is where the API exists that we will use to write like a server and an application. And it's the case that the API to the top level of this stack will implicitly do stuff with all of these lower layers. And so for that reason, I want to at least speak to them a little bit, in part because if you start digging through the code, you'll see stuff in there, vocabulary related to these lower layers, and it helps with debugging to know kind of what's going on there. But we won't spend a ton of our time going through each of these layers in detail, not because it's not interesting, and not because I wouldn't necessarily love to do that, but because I don't think that's the most productive conversation to have right now as you start your final projects. Okay. And I'll mention too, this is the first time that I have given a talk on Bluetooth. It's a challenging lecture to give. There's a lot of content in this class where the mechanism by which you present it is sort of, there's a clear way to present it. This one's a little trickier. There's a lot going on here. There's a lot of different layers, so I'm going to take my best stab at it, and if folks have feedback with regard to how this could be done more clearly, just let me know. So let me start by just giving you a very brief overview of this whole stack. Perhaps it stands to reason that at the very bottom of this stack there exists what the documentation will call the physical layer. This is where the actual 2.4 gigahertz radio lives. Bluetooth is it makes use of 2.4 gigahertz radio. That suggests the existence of some analog circuitry and an antenna and so forth. All of that lives down here at the physical layer and interfaces directly with the link layer. The link layer is controlling the radio in real time, so it's maintaining the state of the radio, and then as digitized stuff is coming in through the radio, it is structuring packets, doing things like computing checksums and encryption sequences and so forth, and providing sort of the lowest level digital interface to that analog equipment down here at the radio. Directly above that is a layer called the host controller interface. And you will see in most implementations of the Bluetooth stack that this is sort of split. The host controller interface is the interface between what the documentation often refers to as the controller side of this stack. This is where the real-time radio stuff is occurring, and the rest of this stack, which tends to have less real-time constraints. And so it's a handy place if you're going to design, say, a Bluetooth chip, like the CYW43 that's used on the Pi Pico W. It's a handy place to sort of split this stack and say, okay, all this stuff is going to take place on the Bluetooth chip itself. Everything above here is going to take place on whatever embedded device is interfacing with this thing. In our case, it's the RP2040. And so if you dig into the documentation, what you will find is that BTstack on the RP2040, the Bluetooth stack that exists on the RP2040, provides you an API to access the layers of this stack down to the host controller interface on the host side. You can send some commands, incidentally, over to the Bluetooth module if you actually care to, but the stack really provides an interface down to here. From here down is largely on the Bluetooth chip, and that's not uncommon. So this is our lowest level interface to sort of the real-time stuff over here. Above that is the logical link control and adaptation protocol, the L2 cap layer. What this is largely doing is taking packets of a very specific size from the physical layer and the host controller interface and putting them together into the larger packets that may be used by your application code. So it's fragmenting packets, big packets that are coming from the top of the stack. It breaks them into little pieces for use down here by the the controller side, and then the stuff coming in, it reassembles them back into packets that make sense to our application code further up. And then above that, and this is where we're going to spend most of our time, having a conversation, there's a layer called the attribute protocol, and on top of the attribute protocol is the generic attribute profile. This is what we're going to be talking about today. This is an implementation of a client-server attribute based on this data type that we're going to spend some time discussing here in a moment called attributes. On a Bluetooth server, the smallest quanta of data, the way that data is actually represented in the server is by way of this data type called an attribute that we'll spend some time describing. There's also some higher level layers here like a security manager, which you may or may not make use of. And then the mechanism by which Bluetooth devices discover the existence of other Bluetooth devices is by way of this other high-level layer that we'll spend some time discussing about today or perhaps on Wednesday, called the generic access profile. So as I said, I'm telling you all of this largely to expose you to some vocabulary so that in the event that you're going through the stuff up here, the API, and you see some vocab related to these lower levels, you at least have some context for that. But as I said before, we're going to be making most use of BTstack's API for the generic attribute profile and the generic access profile, GAP and GATT. We're going to use the GATT API in order to build a server that we can connect to from a client. For instance, your phone or your laptop or whatever it may be. Let me just mention before I go on much further that the stuff that I'm going to present today is a stripped down version. Oops, it's a cancel. It is a stripped down version of a web page that I pointed you to earlier, but let me just point you to it again. On the course web page, there's a page here called GATT server on Pi Pico W. There's a whole demo here, and then the rest of this web page describes how to implement that demo. So in the event that you wanted to build a Bluetooth interface to your final project, I'd strongly encourage you to start by reading through this. I'm going to be talking through it today, but I stripped it down for purposes of our conversation. This is where all the details live. I'll mention too that there is another web page that, unless people would like for me to talk about it, I don't plan to necessarily spend lecture time talking about, which is how we can also make the Pi Pico W a Bluetooth client so that it can play the role that is often played by your phones, for instance. I'd be happy to talk about this. The only reason that I am not necessarily planning on talking about this is that based on final project proposals, it seems like anyone that's going to be doing a Bluetooth thing is probably making a server. So that's what I want to make sure that we talk about. But that's here, and I just wanted to show it to you to remind you of its existence, and in the event that it's useful, you know where to find it. Okay, so then, like I said, one of the things that we would have to understand if we're going to interface our application code with some other third-party library is what it looks like to our application code and the hardware resources that it actually uses. So if you dig down to the bottom of this BTstack, you will find the actual, no kidding, RP2040 hardware that is consumed by this Bluetooth stack implementation. What it actually consumes, when you dig down to the bottom, includes 2 PIO state machines and 2 DMA channels. It turns out, incidentally, that the interface to this external Bluetooth chip is a SPI channel. I think it's actually a QSPI channel. But in any case, they have chosen to implement that SPI interface by way of PIO state machines rather than the SPI peripheral like we used in Lab 1, so that that peripheral remains available to user application code, right? So there's a PIO SPI implementation down there at the bottom, and then there's 2 DMA channels that feed that PIO state machine. The SDK uses that claim mechanism to obtain both of these PIO state machines, which helps with regard to compatibility with your application code. So that is to say, the SDK does not say, give me PIO state machine 1 on PIO block 1, for instance. What it says instead is, please give me one that's not being used. And it does the same thing with the DMA channels. So if you are also using the claim mechanisms in your application code, you don't necessarily have to worry so much about using a resource that is already being used by BTstack, unless you're using like all the PIOs or all the DMAs, okay? So it's useful to just be aware that these are the resources that are actually being consumed. You could also, I suppose, bump into a compatibility issue if you set up BTstack first and it uses the claim mechanism to grab 2 unused DMA channels and an unused state machine on a PIO block, and then your application code specifies exactly which DMA channels you want and exactly which state machines on a PIO block that you want, and you accidentally grab the ones that have already been claimed. Right? So you could bump into a compatibility issue there, something to just be aware of. And then, as I mentioned, the external chip itself implements the physical layer, link layer, and the controller side of the host controller interface. Everything else is implemented on the RP2040 by way of BTstack. There is a link here for some documentation on BTstack, just by the way. Okay. So what does this library look like? Like I said, I'm going to try to only explain this to the extent that it's useful for our conversation. So what does this library look like to our application code? Well, to our application code, what BTstack looks like is an asynchronous event generator. So this code that lives over here, it generates events asynchronously. Of course asynchronously, because this is communication with some external thing. We don't know when packets are arriving, for instance. If you actually dig down under the hood, if you're curious to learn how it actually implements this whole sort of structure, there's something inside of BTstack that the documentation refers to as the run loop. This is essentially a linked list of event generators to go check. So for instance, for every data source, there would exist a linked list item in this run loop for which there's a function that they can go check to see if any data has arrived from that particular data source. You can add timers if you want to this run loop. And the RP2040 port of this BTstack run loop makes use of a high-level Pico SDK library that you may have bumped into called the async context, which to my understanding was, I think, actually written by Raspberry Pi in order to generate compatibility with this. But it's now also used in the LWIP implementation as well. So in any case, BTstack is just churning through all the stuff that might generate events, checking if there's any events that may have been generated. In the event that one is, that generated event becomes visible to our application code by way of a highly structured packet, a big character array. And that character array includes some identifying information. Here's the type of packet that I am. And then it has a payload, right? So it can come up and that packet becomes made available to our application code by way of packet handlers that we write. And so that is the interface between our code and this third-party library. The interface is these packet handlers. We tell our application code what to do with packets of various varieties, and we tell it what to do with those packets of various varieties by way of these packet handlers, which really just look like functions, that we tie into BTstack. We're going to look at this at code in a moment, obviously, but you know, sort of in the abstract, for each of these events, there's a field that is a pointer to a function. When we initialize this whole thing, we're writing the function and passing in the pointer to say, oh, here's the thing to do whenever you encounter a packet like this, right? And then by way of those packet handlers, this stuff gets made available to our application code. I guess before I move on, like I said, I'm not spending too much time talking about each of these layers. I will just mention one kind of interesting feature of all of them. We're going to spend most of our time talking about, you know, GAP and GATT. And what you'll notice when I talk about this is that there's an asymmetry in these layers. It is way easier to be a server in a client-server relationship that I'm about to describe than it is to be a client. The client who's connecting to a server has no idea what the contents of that server is. It has to go through and learn the whole structure of the server, probably, in order to start communicating with this thing. The server, on the other hand, is just always doing what it's told to do by the client. It's just responding to commands, basically, right? But it doesn't have to generate any kind of understanding of some other device or any understanding of anything that exists outside of itself, all it has to do is do what it's told. So there's sort of an asymmetry in that layer. You'll see the same asymmetry when we get to our discussion of the general access protocol, the mechanism by which different Bluetooth devices discover and connect with one another. It's a lot easier to be one of the devices that is advertising that it can be connected to than it is to be a device on the other side of that relationship that's looking for other Bluetooth devices than connecting to them. So one side of this relationship is simple, another side is a lot more complicated. And you'll find that asymmetry in essentially every layer of this stack, and it's by design. This whole sort of communication protocol is designed in order to facilitate communication between relatively high compute stuff, phones, laptops, PCs, that kind of thing, and relatively low compute stuff, heart rate monitors, computer mice, headphones, right? And so it's often the case that one of the two devices in this relationship has a lot more power available to it, is possibly plugged into a wall, has a lot more compute available to it, and the other of these devices has comparatively little. It might be a battery-powered device for which you care a lot about its battery longevity, and so you'd like to not spend a bunch of compute on this thing. It probably has some little microcontroller in it, kind of like the one that we're using, in this class. And so the asymmetry is by design so that we can dump most of the hard stuff to one of the two devices in this relationship. The server that we're going to be talking about is on the comparatively easy side of this relationship. That, like I said, is often the side on which you find microcontrollers, for the obvious reasons. It's often the case that the microcontrollers are in little battery-powered embedded devices that are connecting to phones, laptops, etc., right? And so that's why that asymmetry exists. We'll see that asymmetry come into play. Okay, so as I mentioned, so let me just summarize once more. Okay, so we are trying to generate an understanding of BTstack so that we can design for compatibility. What that requires is that we understand what hardware resources this thing consumes. It consumes 2 DMA channels, 2 PIO channels, and of course a bunch of flash memory, okay? And we have to understand what it looks like to our application code. I've waved my hands at this a little bit. We're going to see it in detail in the code here in a little. But what this mostly looks like to our application code is an asynchronous event generator that ends up calling packet handler callback functions that we write and tie into the rest of the stack. Okay? So we're going to spend most of our time talking through this GATT layer. If we want to build a GATT server, we could have this conversation in a few different ways. But to me, the way that this makes the most sense is if we want to build a GATT server, we need to build a database. So that is to say, we want for our RP2040 to maintain a database of information. Maybe it's measurements from a heart rate monitor or whatever it may be. And in order to build a database that is compatible with a client with which we might connect, we have to structure that database in a very specific way. And so that's what I want to talk about here in a moment. The BTstack external library provides a really handy tool for generating these databases such that they are compatible with the client devices with which we're connecting. And we're going to talk about that as well. But I want to spend just a little bit of time talking about how these databases actually look and how they're structured. So I'll just remind you that when a Bluetooth client connects to a server, it doesn't know anything about the server with which it connects. There might be just a little bit of information contained in its advertising packets saying like, I'm a heart rate monitor or whatever it may be, but it does not know the details of the whole database. It is the responsibility of the client that's connecting to that server to learn all the stuff about that database that it has to learn. In order for that process to take place, perhaps it stands to reason that the two devices in this relationship need to be speaking the same language. So they need to have an implicit agreement with regard to how data is structured and organized in the database on the server side. And they have to agree on how that data is actually accessed. So the way that the client organizes the data in its database is by way of what the documentation calls attributes. An attribute is the smallest unit of information that you will find in a database. And it contains the information of interest, heart rate, whatever it may be, and it also contains some meta information about that information. So if this database is a big table, then every line of that table is an attribute, and every attribute contains a handful of fields. Some of those fields are the actual data that we care about. Other of those fields are metadata about the data. So in particular, every attribute contains a handle, which is 2 bytes long. This handle is essentially the address of the attribute in the database. You could think of it kind of like a pointer, though it isn't necessarily or indeed generally actually a pointer to memory. It's instead its address within this database. Okay, so it has a handle. It has a type, which we'll talk about in just a moment, but this type, which is either 2 bytes or 16 bytes, this is a big string of numbers that represents what the documentation refers to as a UUID, a universally unique identifier for that attribute. The Bluetooth standard has a massive library. Let's see, a massive library of a whole bunch of numbers and what each of those numbers mean in the context of a Bluetooth server. So let's see if we can just find an example. I mean, we could point to any of these. Whatever. The idea is these universally unique identifiers, they aren't necessarily randomly chosen numbers. In the event that attribute, that line of the database represents heart rate, you would go to this big table, find the universally unique identifier for heart rate, and you would plug that number in for the type field of that particular attribute. The advantage of that is every client device, every high compute device, your computer, your laptop, etc., it knows all these universally unique identifiers. And so when it makes a connection to a database and it says, hey, tell me about your attributes, it can look at each of those UUIDs and it goes, oh, okay, this device contains heart rate and temperature and methane concentration or whatever the hell else it might be serving. And it can do things like you may have had the experience of connecting to a Bluetooth device on your phone and it populates like a little icon for headphones or a little icon that represents a heart rate monitor. That's how it's through these UUIDs that it knows what the data in that attribute actually represents, what type of data that it is. We'll see examples of this. Every attribute, of course, also has a value field that holds the data itself. And as we'll see, for some of these attributes, that value field represents like an actual piece of sensor information. Others of them might include organizational information about the database. We're going to see in just a moment that these databases are organized hierarchically. And so there don't only exist attributes for holding the actual data that we're going to be communicating between two devices. There are also attributes that hold organizational information about the database. And then every attribute also has associated permissions, so the connecting device knows whether it is allowed to write to that attribute. Can it only read to that attribute? Does that attribute require any kind of authentication or authorization? So you can have security associated with different of these attributes. So that, like I said, this is the smallest, this is every line in our database is one of these. Some of these contain the actual sensor information that we care to communicate. Others of them contain organizational information about the database itself. All of these attributes are organized into an attribute database, which, as I just said, is hierarchical. The attributes are organized into categories that the documentation refers to as services. Each of these services contains 0 or more characteristics, and each of those characteristics contains 0 or more characteristic descriptors. And everything that I just mentioned is actually an attribute. It's just by way of those UUIDs that we know which of these things that particular line of the database represents. So you can think, it's an appropriate analogy to think about these services as being kind of like classes in object-oriented programming, right? So it's a whole thing, and associated with that service, if it's a standard service for environmental sensing or whatever, there's a certain number of characteristics and characteristic descriptors that are portable and associated with that particular service. And so I thought what might be instructive is to use the BTstack infrastructure in order to build up one of these attribute databases. And I thought perhaps it would be helpful to first of all just take a look at sort of what this ends up looking like. And we're going to, of course, go through this in detail, but this would be a good representation of what an attribute database may look like. They're well organized as tables. Every line in this table represents an attribute. And you can see that every attribute has a length, it has access permissions, it has a handle, that's sort of its address in this table. It has a type, which is a UUID, and it has a value. And the way that this is set up is we start at the top of this table, and if we encounter a UUID for a service, which I'll just remember is I'll remind you is sort of the highest level of this hierarchy, right, in the organization of data here, then everything that appears beneath that declaration of the service is a part of that service until we get to the next line that indicates the beginning of a service. So for instance, the first line here is declaring a service, specifically the GATT service. We'll talk about this a little bit, but it's some service. And then beneath that, we see a second attribute. This one is a characteristic declaration, and as its value, it has the UUID for a device name. So what these two lines are saying is, I'm declaring a service, I'm declaring a characteristic that is a part of that service, and the characteristic that I'm declaring is device name. The next attribute in this line contains the UUID for the device name, and its value is the actual name of that device. So every characteristic has a declaration, and then it has its associated value. Some of them also have descriptors. But we're still in this same service, okay, until we get to this next line, handle 4 here, which contains the same UUID as the first line. So this is another primary service declaration. This is now a declaration for a GATT service, which again we'll talk about, but it's another service. And beneath this, we see more characteristics associated with that service. So we see UUID 2803 again. This is another declaration of a characteristic. This one is declaring the characteristic for a database hash. And then directly beneath that, we have an attribute that actually represents that database hash with the associated UUID. And then the value here would be a 128-bit hash value computed from the database structure. I'll just mention incidentally that the purpose of that particular characteristic, BTstack computes it automatically, but in the event that I'm a client and I connect to a server, I learn its whole database structure and then I disconnect and reconnect. I can check my stored value for this hash to see if anything's actually changed. And if nothing's changed, then I don't have to go through all the work to figure out this database again, right? So that's the general structure though. So then you can see another declaration of a primary service. This is what we're going to spend most of our time talking about. This is a custom one, you know, where we're deciding some specific characteristics to do specific things for our particular project. We give it some name that is not already in the big table of valid Bluetooth IDs. We hallucinated some UUID for it, right? And then we add a bunch of characteristics. And this is what is going to be the bulk of our conversation. The way that BTstack allows for the user to actually build one of these databases is by way of a text-based description of it that looks like this. And so this is the BTstack view of the database that we were just looking at in a more tabular view. And so it's from this text-based description of the database that BTstack will actually compile and generate a database that matches what we describe here. And so we're going to go through this line by line, but you can see that it largely mirrors the structure that we were just looking at before. There's service declarations, and underneath the services, there's characteristics. So there's our GATT service declaration. There's our device name characteristic. Okay. There's our GATT service declaration. There's our hash characteristic. Here's our custom service declaration, and then you'll see beneath this a whole bunch of custom characteristics, stuff that we are adding to the database for our own purposes. And as I'll point you to in just a moment, the way that this works is we build a file that looks like this, And then there exists in the SDK associated with BTstack a Python compiler that will take this text description of the database and it builds a C-compatible. The database ends up looking like a big car array, big character array, right? But it's structured in agreement with the text-based description that we offered. Actually, let me just show you that for just a second. So, for instance, here is a .gatt text file that describes the database that we would like to have compiled. When we click compile, so long as we have the right little command here in CMake list that says, hey, please generate a GATT server from this file. If we do that, then among the compiler generated files, there will be a little folder here called generated that includes a big character array called profile data, automatically gets named profile data, that contains, this is the database associated with that text-based description, right? So this is what it gets compiled down to. We're going to go through the exercise here in a moment of looking at a few lines of these and understanding exactly what each of these represents. It may bother you some of you incidentally, that this is labeled const, which seems to imply that our program code will not be modifying any of the values of this database. Well, then how can the server actually write data to it if we're not modifying it? We'll look at that in just a moment. It turns out that those values for which we want to be able to dynamically change, we label them in the table with a keyword called dynamic, which says, please redirect any request to this attribute to these callback functions so that we can modify these things. The actual data will live in some variable outside of this table. We'll see that in just a second. Any questions about this so far? I fully appreciate that this is sort of a lot relatively quickly. It's a challenging thing to present because like so many things in this class, it makes sense all together, but you have to present it in some sort of a linear order, right? And so it can look a little bit daunting until you start to poke around with it and play with it as a coherent structure. Okay, so then, let's look at this. We're not going to go through every line here because it gets a little bit repetitive, but I do think it's instructive to look at a few of these lines. Okay, so you will note that the first line here of our text description of our attribute database is a service declaration for a GAP service. As it turns out, this is important to note, this is a mandatory service. If you're writing a GATT server, you must have this service in order for your device to be connectable. It has an associated UUID. But what we will note is after we compile this text description into our database, which we were just looking at, this whole database here, the comment here tells us that it's this first line that actually represents this attribute. And so what does the compiler turn that text into? It turns that text into this line in our database. And we can go through this line, and what we will find is all of the fields that should compose a well-formatted attribute. So in particular, if we start over here at the left, we'll see that the first 2 bytes there are, and this is sort of a least significant bit, or most significant bit first thing, so you kind of have to swap orders a little bit, but okay. So the first 2 fields are 000A, 000A, that's 10 in hex. That represents the length of the attribute. So you can count off 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the length of that line. So that's the length of that attribute in bytes. The next 2 bytes that we see are 0002. These represent the access permissions for this particular attribute. And we can go to the Bluetooth documentation and see a table of what numbers represent different access permissions. And what you will find is that 0002 means this attribute is read-only by anyone. There's no security associated with it, but nobody can write to this attribute. It's read-only. We go to the next little set here, and we see 0001. That's the attribute handle. This is the first line of our database, so its handle is 1. Its address in this database is 1, the first line. So you can think about these attribute handles as sort of representing the line of the attribute in the database. The attribute UUID, its universal identifier, is 2800, which is from the Bluetooth specification, we could go to that big table, and what we would find is that 2800 is the UUID for a primary service declaration. So what that tells any connecting device is, hey, this line is me declaring a service, and the final attribute here, 1800, is another valid UUID that comes from the Bluetooth specification, this big table. This one is associated with a GAP service. So this first line of the attribute says, I'm declaring a primary service. The particular service that I'm declaring is the GAP service. This is a service that allows for our device to be discoverable and connectable and so forth. We don't actually have to manage this. This is managed for us automatically by BTstack. The only stuff, as we'll discover, that we have to manage is our custom stuff that we add. This is all managed automatically, but we have to include it. And so you can see that this has generated a line, and it's also, the compiler also generates some handy little macros for us that we'll use later on. You can see that it generates a macro called att service gap service start handle, and it gives us the handle of that service. And it also gives us the end handle, which, as we'll see in just a moment, that's going to be the address of the end of this particular service declaration. That's going to be helpful for tying this database to our actual application code. We're going to make those connections by way of these handle references. But we'll see that in a little bit. Okay. The next line of this server is a characteristic declaration. And in our text-based description of this database, we sort of convolve two attributes that then become apparent in the compiled version. So what we're saying in the text-based version here is, hey, I would like to create a characteristic, specifically the GAP device name characteristic, make it read-only, and I'd like for its value to be Pico server. When we actually look at what this gets compiled to, what we note is that two attributes appear in our database. The first of these is a characteristic declaration. So that would be the first of these, characteristic declaration. And we can go through sort of the same exercise here to convince ourselves that what we're actually seeing is a well-formatted attribute that makes sense. It's been added to our compiled table. So as before, you can see the first 2 bytes of this are the length. This one is 000D, 000D. That's the length of this. You could count up those bytes and confirm, oh, yep, it's that long. Its access permissions, read only by anyone again. Its handle is now 2, right, because we're in the second line. Its attribute type is 2803. That's a number that we could go look up from the Bluetooth standard. That is the UUID for a characteristic declaration. So we'll see that a bunch of times in our table because we're declaring a bunch of characteristics. And then the value is the UUID of the characteristic that we would actually like to create. And in this case, it is 2A00, which happens to be the ID associated with the device name characteristic. Okay, so that's the first server that gets created, or the first attribute that gets created. The second one is the attribute that actually holds that characteristic. And we could go through again, and of course, this one also has a length. It has access permissions. It has a handle. We're now at line 3, so its handle is 3. It has an attribute type. This one is the UUID associated with device name. And then if you were to convert these last handful of bytes into ASCII, what you would discover is that the value of this attribute actually represents Pico server in ASCII. People okay with this? Okay. So like I said, we won't go through all these things, but let me just hit some that are instructive. So that was declaring a sort of a standard service and a standard characteristic. I'm going to skip over this because this is creating yet another standard characteristic, or yet another standard service and yet another standard characteristic. Let's get to kind of the juicy part, which is making a custom primary service. So it's by way of what I'm going to spend some time describing here, that you could make a fully custom Bluetooth server device tuned to your specific project. If you're making a Bluetooth controlled synth, you could make a characteristic that for you means frequency. User can enter some frequency and the frequency appears coming out of the synth, for instance. Or if you're a video game, you could have buttons meaning up, down, left, right, whatever, right? So it's by way of this that you actually design a Bluetooth server that is tuned for your specific purposes. But it looks a lot like what we've already seen. So this whole process starts with us declaring a primary service in contrast to what we saw before when we created a primary service. Sorry for all the scrolling. You can see that previously when we were making standard services, the BTstack allowed for us to just provide the name of that standard service, and the compiler knew what we were talking about because this is a standard service. So we say, hey, I'd like to make a primary service, specifically the GATT service. I'd like to make a primary service, specifically the GATT service. Now, however, we're going to make a custom service, and so we say, I'd like to make a primary service. Here's the UUID I'm going to use. It's not a standard one. It's not one that's already been consumed by other like Bluetooth stuff. We've generated one here, and we're saying I'm declaring a service just like previously. Here's its UUID. Because it isn't standard, it can't just go look up whatever the UUID happens to be. So here, we're telling you what it is. And then like before, and as we'll see, we're going to go through and add characteristics to our service. And we are also going to add characteristic user descriptions to our service, which I'll show you in just a moment. This makes them a little easier to interact with. Okay. And the pattern's going to repeat. So you'll just see our custom service includes a service declaration, a characteristic declaration, a characteristic user description, and then it repeats a characteristic declaration, a user description, a declaration, a user description. And we're going to be adding 1, 2, 3, 4, 5, 6 characteristics to our service. So I'm going to talk through about this in detail. Is there anything else I'd just like to mention at a high level here before we move on? Those access permissions associated with each attribute, you find that those are specified in sort of the second or third argument here to each of these characteristics, where you can see read there, write without response, read, etc. That's us specifying the access permissions for that particular attribute. Notify we'll talk about, but what we'll see is that this is specifying that this particular attribute, the client can turn on notifications for that. And if the client turns on notifications, then what that means is if the server changes the value in that attribute, say it gets a new measurement from a heart rate sensor, and we've turned on notifications, then the server will automatically tell the client. The client doesn't have to request the new information. The server will just automatically, every time it changes something, it spits out the new information. That's kind of handy for streaming stuff, for example. The dynamic field here, we're going to look at this in more detail as well, but what this specifies is that we would like BTstack to send any read or write requests for this particular characteristic through a packet handler to our application code, where we will handle it in our program. So this is telling the Bluetooth stack, I would like to be responsible for managing this characteristic. Dynamic means every time the client requests to read this, tell me, I will handle that. Which is necessary for this custom stuff, right? Because how would it know how to handle that? So that's what that means. So we're essentially out of time. I'm going to continue this story next time. I think by the end of next time we can get through this whole thing, and then we'll carry on with some other sort of special topic stuff. I hope this stuff's useful. For those of you, again, for those of you that are building Bluetooth interfaces to your projects, I strongly encourage you to go through that web page that I pointed you to previously, and and I'll be happy to try to answer questions. There's a lot going on here. Okay, I will be in lab this afternoon. I'll see many of you then. I'll see the rest of you on Wednesday.